Hello children, today we talk about gas laws. The main parameters which characterize a gas are volume, pressure, temperature, number of moles, such as if I have a gas in a cylinder having volume V at pressure P and temperature T, how many moles are there? So to relate all these parameters, there are some gas laws. The first gas law is Boyle's law. Boyle's law. Boyle's law relates pressure and volume at constant temperature. To discuss this law in detail, first let us talk about a gas cylinder fitted with a piston. Suppose this is filled with a gas at volume V. So let this is the initial volume. Suppose this is V1 and the pressure acting on the piston, let this is P1. So P1 is the pressure on this gas and the volume of gas is V1. Now suppose if I start increasing the pressure, when I increase the pressure on piston, the piston will start moving in downward direction. Let us the new position of piston would be after applying pressure is this one. Now, this is the direction of movement. Suppose now the pressure becomes P2. So now children, it's clear to you that on increasing pressure, the volume of gas reduced. Initially it was V1. Now it becomes V2 and it's very much clear from this diagram that the value of V2 is less than V1. So here the relation is coming between pressure and volume. Such a simple thing, no? That when I start increasing pressure, the volume starts decreasing. It means we can say pressure and volume, they are inversely proportional to each other. So Boyle says that at fixed temperature, the volume of certain mass of gas is inversely proportional to its pressure. Got it? I'm repeating. At constant temperature, volume of given mass of gas is inversely proportional to its pressure. Understood children? Now, if I remove the sign of proportionality, I may write V equals to K upon P or PV equals to constant. Keeping one thing in your mind, temperature should remain constant. We cannot change this. Only then we can relate pressure and volume. So, it means the product of PV always comes constant. So, we can write P1 V1 equals to P2 V2 and so on. Whatever the number of readings you can take, the product of pressure and volume always comes constant. This is the relationship between pressure and volume at constant temperature given by Boyle. Now, how do we represent it graphically? To plot a graph between pressure and volume, as we know, they are inversely proportional to each other. So, when I plot a graph between pressure and volume, the graph comes something like this. That when I start decreasing pressure, volume keeps on increasing. And the condition for this graph is constant temperature. So the plot between pressure and volume at constant temperature is termed as isotherm. Yeah, children. What do we call it? This is termed as isotherm. Now the next graph. Plot P with 1 by. We know P and 1 by V. It's clear. They are directly proportional. Right now, volume and pressure are inversely proportional, but volume and 1 by P, they are directly proportional. So, the graph will come like this. Condition again remains same, constant temperature. And third, we can plot a graph of PV versus V, or you can take pressure divided on x-axis. So, yes, would the graph will be like this or like this, children? Try to tell. No, not possible. Neither this one nor this one, because just look this relationship. The product of pressure and volume always remains constant. So whatever the value of V, this product cannot change. It will always gives us a constant value. So the graph will be like this. Straight line parallel to x-axis means no change. Whatever the change in volume we can do, this product always comes constant. Clear? I am giving you one more graph between pressure and volume. This graph is given in NCERT. The three graph. This is first one. The temperature given here is T1. The second one, for this given temperature is T2. And the third one is T3. Somewhat like this. This graph is given. And the question is, what is the relation between T1, T2, T3? Increasing order, decreasing order, or are they equal? Right? These are the options. Decreasing order. Now children, in this case, all the three are variables. Means pressure, volume, temperature. In previous graph, we were keeping temperature constant. That was so easy to relate. But here also very simply we can relate when three variables are given. Keep any variable constant. Like if I am keeping pressure constant. For example, I am taking this pressure. At this pressure, now I want to check the values of V and T. Simply, this is the volume corresponding to T1. This is V1 corresponding to T2. This is V2 and corresponding to T3. This is V3. So simple. Now answer is with us that when volume V1, the temperature is T1, V2, T2, V3, T3. So in this direction, V1 to V3, volume is in increasing order. And we know when volume starts increasing, of course, temperature will also increase. So it's clear when V1 to V3 volume is in increasing order, then of course temperature will also be in increasing order. So the correct relationship is this is in increasing order. So this is the way to decide when all the three are variables, keep one constant and then you can easily relate the others. So this is the direction, that increasing order of temperature. Yes, now this concept of Boyle's law is clear. Take one question so that we can apply this law now. Yes, the question is, what will be the minimum pressure required to compress 500 decimeter cube of air at 1 bar to 200 decimeter cube at 30 degrees Celsius? So children, note down what all parameters are given to us. The first parameter given to us is 500 decimeter cube of air. Means we take this V1 Initial volume 500 deciliter. At 1 bar pressure, we take this as P1, 1 bar. Up to how much? Compression 200 decimeter cube. So this is V2 equal to 200 decimeter cube. Next, at 30 degrees Celsius, means they are keeping temperature constant. Now, easily we can decide if temperature is constant, which law relates pressure and volume? Of course, that is Boyle's law. So, now apply the relation for Boyle's law, that P1 V1 equals to P2 V2. Substitute the values. Initial pressure 1 bar. Initial volume 500. Final pressure, that we need to find what will be the pressure. So P2 we have to find into V2 200 decimeter cube. So the answer for P2 will be 500 divided by 200. That will come 2.5 bar. Easy to decide. One thing which is very important while doing the numericals, which generally students don't pay attention. These things are first very important to use formula. Generally students they start straight away. No, because you will get marks for each and every step. So don't forget to write the formula. And the second very important thing, generally students they don't use unit for answer. So after finding the answer, always write the unit. Right? So in this way you can solve the questions based on Boyle's law by using the relation P1 V1 equals to P2 V2. Now the second law is Charles' law. Charles' law gives the relation between volume and temperature. Volume temperature relationship at constant pressure. Again, take a gas cylinder fitted with a piston. Pressure on this piston is P. Let us take the volume of gas filled in this cylinder, V, or if I take initial volume as V1, because I have to relate volume with temperature, I need to check on changing temperature how volume changes. And this volume of gas V1 is at temperature T1. Now if I start heating the gas, I start heating the gas. On heating the gas, particles, their kinetic energy starts increasing, and if kinetic energy increases, the movement of particles starts increasing. So they start moving away from each other. So due to this, what happens? I cannot change the pressure because the condition is keeping pressure constant. So when I start heating the gas, due to increased kinetic energy of particles, they start moving far away from each other. So what would happen? As a result, volume starts increasing because we cannot change the pressure. So the piston will move in upward direction. Means suppose it reaches here now. So it means now the volume becomes V2, that is higher than V1. Now relation clear between volume and temperature, that when I start increasing the temperature at constant pressure, volume starts increasing. It means volume and temperature, they are directly proportional to each other at constant pressure. So we may write volume is directly proportional to temperature. Again I am repeating the thing, keeping pressure constant. So remove the sign of proportionality. We have a constant V equals to kT, or I may write ratio of volume and temperature always remains constant, means V1 by T1 equals to V2 by T2 and so on. Again, very easy, no? You can relate this graphically also. If I plot a graph between volume and temperature, as they are directly proportional, so straight line starting from origin at constant pressure. So a plot of volume and temperature at constant pressure is termed as isobar. Yeah, children. Now this is clear how we are relating volume and temperature by using Charles' law. Another way to represent Charles' law is that with each degree rise in temperature, which each degree rise in temperature, volume of given mass of gas increases by 1 by 273.15 parts of its original volume at 0 degrees Celsius. Clear? This is another way to express Charles' law, that with each degree rise in temperature, volume of given mass of gas increases by this much parts of its original volume at 0 degrees Celsius. Suppose we take the volume at 0 degrees Celsius is V0, is its volume at 0 degrees Celsius. Now if I increase temperature by 1 degree, on increasing temperature by 1 degree Celsius, now it's how much volume increase? That is 1 by 273.15 parts of original volume. This much increase in volume we will observe. Similarly, if I increase the temperature by 2 degrees Celsius, multiply this by 2. Now for general expression, let us increase the temperature by T degrees Celsius. Suppose I am increasing the temperature by T degrees Celsius. Now on increasing this much temperature, suppose the final volume becomes Vt. Now what will be the value of Vt? Vt is equal to initial volume, that was V0, plus the increased volume. This much part multiplied by the temperature, because for every degree this much increase is observed. So V0 upon 273.15 into the rise in temperature. This is the final volume of gas becomes. Further solve this. Vt is equal to, V0 is common, so we will be having 1 plus P by 273.15, or we may write Vt equals to V0 273.15 plus T divided by 273.15. Here comes another relationship. This 273.15 plus T, this is temperature in Kelvin. So this is the relationship between degree Celsius and temperature in Kelvin. So this is thermodynamic scale of temperature. This Kelvin scale is termed as thermodynamic scale of temperature, or we may call it absolute scale of temperature. Absolute scale of temperature, or simply Kelvin scale. For all scientific works, we take temperature in Kelvin, we never take temperature in degree Celsius. Understood how to convert temperature in degrees Celsius to temperature in Kelvin. To make the calculations easy for the sake of simplicity, we may take simply 273 at the place of 273.15. Now children, and in this equation, if I substitute temperature as minus 273, so just check what will come on placing temperature as minus 273 degree Celsius. So when I take temperature minus 273.15 degree Celsius, on substituting this value here, volume comes 0. dT comes 0. 0 volume means gases cannot exist at this temperature. Does not exist at this temperature. So this temperature minus 273.15 degrees Celsius or 0 Kelvin, right? Or 0 Kelvin is termed as absolute temperature. This absolute temperature is the hypothetical temperature before this all the gases are converted into liquid. That's why gases cannot exist at this temperature. Understood children this thing? Now I'm giving one graph, that is relation of pressure and volume, but the graph is something like, volume and temperature, because we are taking Charleston. So the graph is something like this. At P1, P2, P3, P4. Means again all the three parameters are variables. We are not keeping any parameter constant. And again examiner is asking the relationship between P1, P2, P3 and P4. Increasing order, decreasing order, or are they equal? So as I told you in previous part, that whenever all the three are variables, keep one parameter constant so that easily you can decide the relation for others. For example, if I'm keeping temperature as constant, let us take this temperature. This is constant temperature. Now take the value of volume and pressure corresponding to this temperature. This is for the first one, P1. Let us, this is V1. P2, so V2. P3, V3. And P4, V4. Yes children, now I think till now you must have decided the relation between P1, P2, P3, P4, that V1 is maximum value. If V1 is maximum, understood, P1 should be minimum, because we know volume and pressure, they are inversely proportional to each other. It means if V1 is maximum, P1 is minimum, and V4 is minimum, so P4 should be maximum. So the pressure is in increasing order. Understood how to solve the questions based on graphs. Third law is Gay-Lussac's law. This law is the relationship between pressure and temperature at constant volume. Now we have to decide what happens when we keep the volume constant and start increasing temperature. To understand this concept, a very common example is coming to my mind. Children, you must have heard many times that on Yamuna Expressway, the accidental cases are really very high. Reason why the rate of accident is too much on Yamuna Expressway. Because when the vehicles are running at very high speed, especially during summer days, the volume of tire is constant, and when the vehicle is running at very high speed, as the volume of tire is constant, temperature is continuously increasing. Now, especially during summer days, already temperature is very high. Temperature is high, volume is constant. Then what happens? The air filled inside tire, it starts exerting more pressure. Its pressure continuously increases. Due to that increased pressure, the tire gets burst. Clear? So main cause of accident is bursting of tire, and reason because temperature increases, volume is constant. So ultimately due to increased pressure, the tire gets burst. So it means now this simple example is giving us a scientific relationship, a scientific explanation that how pressure and temperature are related. This is the main cause behind those accidents. So we can say at constant volume, the pressure of given mass of gas is directly proportional to temperature, keeping volume constant. Or if they are directly proportional to each other, so we may write P equals to KT. K is the proportionality constant. Or we can say the ratio of pressure and temperature remains constant. So we may write P1 by T1 equals to P2 by T2 and so on. Similarly, you can plot a graph between pressure and temperature as they are directly proportional to each other. So graph is similar as we plotted in Charles law, straight line starting from origin. So, and the condition here is volume is constant. So a plot between pressure and temperature at constant volume is termed as isochore. Yes, understood now these three gas laws? Fourth law is Avogadro's law. This is relationship between volume and number of moles. According to Avogadro law, under similar conditions of temperature and pressure, equal volume of all gases contain equal number of molecules. Right, children? That if temperature, pressure and volume, these parameters are same, then the different gases, they will be having same number of molecules. For example, if I'm saying I have 100 ml of hydrogen gas, 100 ml of ozone gas and 100 ml of methane gas. For all these three gases, pressure, temperature and volume, these parameters are same, and the number of molecules of first gas are X, or I can say X1. What would be the number of molecules for second and third gas? Children, apply Avogadro's law that all other parameters are same, number of molecules will also be same. So of course, X1 here and X1 here means identity of gas doesn't make any difference. If all other parameters are same, then the number of molecules would also be same. And if number of molecules are same, means number of moles are also same. So we can say volume is directly proportional to number of moles, or V equals to K into, and K is the proportionality constant, or we can say this ratio remains constant. That is V1 by N1 equals to V2 by N2 and so on. Easy no? Understood this also? Next topic is ideal gas equation. Before this, children, we talked about different gas laws. So a gas which obey all the gas laws strictly is termed as ideal gas. So a gas which follow Boyle's law, Charles' law, Avogadro's law, right? So the equation which follow all the gas laws strictly is termed as ideal gas equation. So what would be the equation for ideal gases? Simply we can say this is a combined form of all the gas laws. So how do we write that equation? Simply use all the gas laws. Like I'm starting with Boyle's law. According to Boyle's law, volume is inversely proportional to pressure, right? Then I use Charles' law. According to Charles' law, volume is directly proportional to temperature. Then I take Avogadro's law. According to Avogadro's law, volume is directly proportional to number of moles. So what would be the combined form of all these laws? Volume is directly proportional to number of moles and temperature, and inversely proportional to pressure. Or I can say PV is directly proportional to NT. If I remove the sign of proportionality, I would be having a constant R. PV equals to nRT. This R is universal gas constant. Universal gas constant. Now children, the most important point here is there is a confusion in the values of R. The commonly used values of R, I am telling you, the one is 8.314 joule per mole per Kelvin. This is the one value of R which we will be using. Other than this, the values are, the second is 0.0821 liter atmosphere per mole per Kelvin. The third value of R is 2 calories per mole per Kelvin. So these first and third value we will be using in thermodynamics. So these are for thermodynamics. Same this one also. In this unit, mostly we will be using this value. So most of the questions we solve by using the value 0.0821 liter atmosphere per mole per Kelvin. Another relationship from ideal gas equation, PV equals to NI. This ideal gas equation is also termed as combined gas law. Because we derive this from all the gas laws, no? As well as this is also termed as equation of state. Now, suppose for a given mass of gas, the initial pressure, volume and temperature are P1, V1 and T1. Now its pressure, volume and temperature, they are changing from P1, V1, T1 to P2, V2 and T2. These are the initial 3 parameters and these are the final 3 parameters. Now from this equation, I may write PV by T equals to NR. For first set of parameters, I may write P1, V1 by T1 equals to NR. For second set of parameters, I may write P2, V2 upon T2 equals to NR. Or from these two initial and final states, I may write P1, V1 by T1 equals to P2, V2 by T2. Again children, very important form of ideal gas equation, P1, V1 by T1 equals to P2, V2 by T2. Next topic we will be taking is relation between density and molar mass. Of gas. This relation we can derive from ideal gas equation. We know ideal gas equation, PV equals to nRT, ideal gas equation or equation of. Now in this equation, we substitute the formula to calculate N. N is number of mole, and we know number of mole equal to given mass divided by molar mass. So if I substitute this value here, I will be having PV equals to, at the place of N, I am taking given mass divided by molar mass RT. Or rearrange the equation, P equals to given mass divided by volume RT by M. Now children, look here, one new relationship is coming. Mass by volume is density. So at the place of this, we can write density. So we will be having P equals to rho RT by M, or density equals to PM by RT. So this is the equation which is relating density and molar mass of gas derived from ideal gas equation. So now we discuss the numericals based on all these concepts. Such as this question given to you is 20 ml of hydrogen measured at 50 degrees Celsius, heated to 35 degrees Celsius. What is the new volume at the same pressure? So now children, just note down the parameters given to you are. First is 20 ml of hydrogen, means initial volume is given to you. V1 20 ml. Next is measured at 15 degrees Celsius. So second thing is initial temperature, which is given in Celsius. If you remember, I told you in theory part that for all the calculations, we will take temperature in Kelvin. So what should I add? Yes, 273. Good answer. So plus 273. Right? So that temperature is converted into Kelvin, that is 288 Kelvin. Then given to us is to 35 degree Celsius, that is final temperature T2, 35 again in Celsius, so 273. So the temperature becomes 308 Kelvin, right? Then what is the new volume at the same pressure? Means we have to measure the final volume. At same pressure means pressure is constant. So now children, decide which law we will be using here. We have to find the relation between volume and temperature when pressure is constant. So this is, yes, good, Charles' law. We will be using Charles' law. So now use the formula of Charles' law. V1 by T1 equals to V2 by T2. Substitute the values. V1 20 ml, T1 288, V2 we have to calculate, and T2 308. Now you solve this question for V2. Yes, you can do this. On solving, you will get the answer 21.38 ml. So I think now this is clear to you. How do we solve the questions based on Charles' law? Now the next question is, an iron cylinder contains helium at a pressure of 250 kilopascal at 300 Kelvin. The cylinder can withstand a pressure of 1 into 10 to the power 6 Pascal. The room in which cylinder is placed catches fire. Predict whether the cylinder will blow up before it melts or not. Melting point of cylinder is 1800 Kelvin. So children, how we will be doing this question now? Again check what parameters are given to you. First given is pressure 250 kilopascal. Then temperature is given 300 Kelvin. So initial pressure, initial temperature, just note down P1 250 kilopascal. Then T1 already given in Kelvin. This is. Then the cylinder can withstand a pressure of this much pressure cylinder can bear. Now, the room in which it is placed catches fire. Predict whether it will blow up before it melts or not. And the melting temperature would be 1800 Kelvin. Again given to you. So the final temperature T2 1800 Kelvin. We need to calculate the pressure at this temperature. If the value of pressure comes less than this pressure, the cylinder cannot blow up, right? But if the coming pressure would be more than this, then of course it will blow up. So we have to relate pressure and temperature at constant volume. So which law is this? Yes, it is Gay-Lussac's law. Gay-Lussac's law. The formula is P1 by T1 equals to P2 by T2. Substitute the values. Initial pressure 250 kilopascal. Initial temperature 300. Final pressure we have to calculate. And final temperature is 1800 Kelvin. So from here again solve this for P2. P2 would be equal to 250 into 1800 divided by 300. Solve it. You will get the answer 1500 kilopascal. This is the answer coming. Now compare this answer that how much pressure cylinder can withstand. This is 1 into 10 to the power 6 Pascal. Just convert this into kilopascal to compare this with the answer. So 1 kilopascal equals to 1000 pascals. So 10 to the power 6 Pascal is equals to 10 to the power 3 kilopascal. It means this is the safe pressure for cylinder 10 to the power 3 kilopascal. But our answer coming is 1500 kilopascal, that is higher than that 1000 kilopascal. It means cylinder will blow up. Right children? So now next question is, at 25 degrees Celsius and 760 mm of Hg pressure, a gas occupies 600 ml volume. What will be its pressure at a height where temperature is 10 degrees Celsius and volume of gas is 640 ml? Again note down the parameters which are given to you. The parameters first is initial temperature, initial pressure and initial volume. These three things are given. So at 25 degrees Celsius, that is T1, 25 plus 273 in Kelvin, 298 Kelvin. Then the pressure P1, 760 ml. Initial volume V1, 600 ml. Now, coming to next statement, what will be its pressure? Means final pressure we have to calculate. Where temperature is 10 degrees Celsius, this is final temperature, and the gas occupies 600 ml. This is final volume. So these parameters P2 we have to calculate. Then T2, 10 plus 273, that is 283 Kelvin, and V2 is 640 ml. Now just try to answer this question, children, that all the three variables are given: pressure, temperature and volume. When all three variables are given, which law we will be using? Yes, combined gas laws, that is ideal gas equation. P1 V1 by T1 equals to P2 V2 by T2. So use this equation and substitute all the values. Initial pressure 760, initial volume 600, initial temperature 298, then final pressure we will be calculating, final volume 640 and temperature 283. Solve this for P2 and the answer is 676.6 ml. Clear this question based on combined gas laws. So now next question. Calculate the number of moles of hydrogen contained in 18 liter of gas at 27 degrees Celsius and 70 centimeter pressure. To check which law we will be using here, again note down all the parameters given to you. So now check which are all the parameters. First, we have to calculate number of moles of hydrogen. So that we need to be solve number of moles of hydrogen we have to find. Now what is given next? Contained in 18 liter of gas, volume of gas is given at 27 degrees Celsius, temperature is given, and 70 centimeter pressure is also given. So these parameters are, first is volume of gas 18 liter, second temperature 27 plus 273 temperature in Kelvin, that is 300 Kelvin. Then pressure P equals to 70 centimeter. So children, what is the relation between number of moles, pressure, volume and temperature? Again, your answer is correct. It is ideal gas equation. PV equals to nRT. So we will be using ideal gas equation. Substitute the values here. But before substituting the values, we need to check the value of R, that is universal gas constant, and we know the value of R is 0.0821 liter atmosphere per mole per Kelvin. It means for this value, we need the volume in liters, that is already given in liters. Pressure should be in atmosphere, but it is given in centimeter. So we need to convert pressure into ATM. So the relation is 1 ATM equal to 76 centimeter. So what is the value of pressure? Now this is P equals to 70 divided by 76 ATM. Right? Now substitute the values. So pressure 70 upon 76 into volume is 18. Number of moles we have to find are 0.0821 and temperature is 300. So N will be equals to 70 into 18 divided by 76 into 0.0821 into 300. Solve it to find the number of moles of hydrogen, and on solving we will be getting 0.67 mole of hydrogen. Understood this thing? Now let us start the next question. Given is what is density of SO2. So we have to find the density. Given is at 27 degrees Celsius temperature, 2 atmospheric pressure. Pressure is also given. So use the relation of density with temperature, pressure. Clear? So the formula is rho equals to Pm by RT. Substitute all the values. The given is density. We have to find temperature 27 plus 273. Remember this, always use 273 to convert temperature into Kelvin. Never use temperature in degrees Celsius. The next pressure 2 atm. R universal constant 0.0821 liter atmosphere per mole per Kelvin. Now substitute all the values. P2, molar mass of SO2, 32 plus 2 into 16, that will comes 64 gram per mole. So 64.0821 into temperature 300. Solve this for the answer of density. You will get 5.19 gram per liter. So these were the different questions based on all gas laws, Boyle's, Charles, Gay-Lussac's, Avogadro's and ideal gas equation. So with this part is complete. I think now all the doubts are clear.